Hello and welcome back to your Organic Chemistry 1 lecture. This lecture, we're going to talk about NMR spectroscopy, which is nuclear magnetic resonance spectroscopy. If you've got the third edition book, this is chapter 15. In the second edition book, it's chapter 16. So just keep in mind and follow along appropriately. We're splitting it into two parts. We've got proton NMR, and then we've got carbon NMR. The techniques are the same, but the outputs are a little different, and kind of the information you get out of them is different as well. So NMR is basically, it's a type of spectroscopy. So again, you have your nucleus and you have electromagnetic radiation. You're shooting it with electromagnetic radiation and you're trying to see what happens to the nucleus. We'll get into the details of that here in a little bit. But basically what happens is with NMR, it's kind of one of our most powerful methods for actually figuring out the structure of compounds. And by the end of this chapter, we hope that you'll be able to take the information from an NMR spectrum and then figure out, hey, what kind of structure do I have here? So yeah, let's go ahead and get started. Okay, so the only types of nuclei that you can use in NMR spectroscopy, the only ones that you can use have to have either an odd number of protons or an odd number of neutrons. Because we are gonna kind of define a quantity here or a particular behavior here, which is called nuclear spin. So the idea is like these particles have angular momentum. Now, if you have an even number of each type of particle, their angular momentums are going to cancel each other out. But if you have like an odd one, so like a proton is a great example, right? Hydrogen, that's what we're going to start with. Hydrogen just has one proton. So there's no way for the angular momentum of that proton to be canceled out. So it has angular momentum. Now, the thing is, a proton, as it's spinning, we think of this as a spin, this angular momentum as a spin. Because it's got a charge, it actually is going to generate a magnetic moment. And so this magnetic moment is going to generate a magnetic field. Now, if the nucleus itself generates a magnetic field, then that's going to interact with external magnetic fields. And that's what NMR spectroscopy takes advantage of, basically. The way we can think about it is like, again, think of a proton like a ball, okay? And it's a big ball of charge and it's spinning, left hand, right hand, however it is. That spinning generates a magnetic moment. And that's kind of how we can imagine it in our heads. The truth is much more complicated. So like, if you've already taken your particle physics and you want to correct me on this, yes, I am admitting this is not how it actually happens. This is just how we kind of think about it and we can map it onto it. If you're curious about it, I can give you a lot of good reading to read up on. And once you get into physical chemistry in the future, you'll learn all about it. But for now, we're approaching it as organic chemistry, and protons are these little balls of spinning charge. So they generate a magnetic field, and that means they're going to interact with external magnetic field. And if you just have a sample of these atoms that are floating around, they're going to be, at all different orientations. But if you stick it in a strong magnetic field, it's going to reduce it to two possible ways that it can align. The nuclei will either align with the field or against the field. So alpha is the way it's pointing up, that's aligned with the applied magnetic field. The beta, that's when it's aligned against. So we think of it as like up or down, right hand rule, spinning up or spinning down. So this is just your definition here. The beta spin state, because it opposes the magnetic field, that's the higher energy spin state, whereas the alpha spin state is aligned with the external magnetic field. So that means it's going to be a lower energy spin state. So alpha is lower in energy than the beta. Now this delta E, that's what's going to be important for NMR. So when an alpha, okay, so if you have so if you have this nucleus that has the alpha spin state and it's exposed to radio waves of the exact right energy to basically add alpha plus this energy to get you to the beta, the photons are going to be absorbed and the spin is going to flip from the alpha state to the beta state. So it's just like what we've learned before, both with IR spectroscopy, where we had molecules vibrating faster, as they absorbed IR radiation. It also recalls atomic spectroscopy, where atoms, electrons in atomic orbitals can absorb photons and be promoted in energy levels. The same thing is the case here, where now we just have these two separate states. We have the alpha spin state aligned with the magnet, the beta spin state against the magnet. And the difference in energy here is equivalent to a particular energy of light. Now, one thing that's crucial here is the strength of the magnetic field is actually going to change this gap as well. The stronger you make your magnet, the bigger the gap is going to be. Okay, so that's important to keep in mind here. Now, what also happens is, so that's one thing, right? We know it's all about the nuclear spin. We align it with or against. But the thing is, if that were the case, and that was it, there was nothing affecting it, it wouldn't be that useful, right? Because all of these spinning nuclei would all show up at the same place and have the same delta E gap there. But of course, that's not the case. Because this external magnetic field doesn't just act on the nuclei that have a net angular momentum, it also is going to act on the electrons, right? Electrons are negatively charged, so they generate their own magnetic field. And so, yeah, so what happens is applying this external magnetic field is going to make electrons circle the atom. And that circling of the atom actually induces an opposing magnetic field. That's what's called a diamagnetic field. So here's our external magnetic field. The electrons circle. This is like around a sigma bond here in particular, which is kind of our most. Now the circling negative charge generates a magnetic field. And that magnetic field is actually going to oppose the magnetic field that the nucleus experiences. So if you have a bunch of electrons, the more electrons you have around a nucleus, the more shielded the nucleus is from the external magnetic field. And if it's shielded from the external magnetic field, it experiences less of an external magnetic field, so it's easier to flip the spin. On the other hand, if you remove electron density, the opposite is true. So that means that it's going to be closer to, it's going to be less shielded, or what we say deshielded, and therefore it's going to be harder to flip because it's experiencing the external magnetic field. Okay, so yeah, so this is what's useful about NMR. Basically, the energy that's required to do the spin flip from alpha to beta is going to depend on how many electrons are around the atom. And that's what's important to us, right? We want to know where the electrons are so that we can predict, what kind of reactions those electrons are going to do. Also, it's a way of determining, if you have a methyl group and you have an isopropyl group, well, the isopropyl group, the single hydrogen on that is going to experience a different electronic environment compared to the methyl group. So it's just a way that you can determine, the different types of hydrogens, and in the future we'll talk about carbons in this sample. Right. Okay. So this is resonance here. Basically, when you apply that correct frequency of electromagnetic radiation, energy is absorbed, the spin flips, and that is the moment that you say that the atom is in resonance, because it's in resonance alpha to beta. Just keep in mind, this type of resonance is not the same as the resonance of the molecular orbitals, like what we studied in chapter 2. This is just a resonance, like it's a resonating, nuclear spin going back and forth. So just keep in mind, don't think of it in terms of resonance like what we talked about before. This is a different type of resonance. And yeah, I already mentioned this here, but the amount of energy required for each proton to flip is going to tell us about the amount of electrons that are around it and its electron environment. And then we can use that to decode the structure of a compound. Yeah, so you do need a very strong magnetic field, and then you're going to use radio wave energy to actually do the flip. The stronger the magnetic field, the bigger the energy gap is going to be. And so basically, like here, if we have a 1.41 Tesla external magnetic field, we have a relatively small gap in energy. And then if we apply, 6 times bigger or 5 times bigger, 7.04 Tesla magnetic field, all of a sudden the gap is much higher. So that's going to require stronger or a higher energy radio wave radiation to figure that out. And if there's no external magnetic field, then there's no absorption in the radio waves because the alpha and beta states don't exist. There's no energy gap between them. Okay, so how do you generate this strong of a magnetic field? Well, what you have to do is you use an electromagnet. So if you may be familiar, it's like you do a coil thing here. I know this is going to be a dated reference here very soon, but if you ever saw, what is it called, Stranger Things, and I think it was season 2, the high school teacher was demonstrating magnetism. And what you do is you just wrap a coil in a circle, and if you pass a current through that coil, the circling electrons generate a magnetic field. And so you can generate a magnet in that way. And you do the same thing with the NMR spectrum, except you do it using superconducting material. The superconducting material allows electrons to circle very fast. And in order to do that, it has to be at very low temperature, around 4 Kelvin, so very close to absolute zero. Generally speaking, you have to use liquid, some combination of liquid helium and liquid nitrogen to get down to that temperature and keep it cool enough. Yeah. Now, the more current you pass in, the more electrons are going to be circling, the stronger the magnetic field is that's generated. Okay, so I'll tell you briefly about the input, how this goes down. There's a difference between the way that this one works and the way that like your UV vis spectrometer worked in Gen Chem 2. If you used a UV vis spectrometer in Gen Chem 2, it probably like slowly scanned through all the different wavelengths and then like read it on the peak. You don't have to do that with NMR, and it's similar with IR. You don't have to do that with IR either. You can just pulse the sample with all of the radio wavelengths that you need. That excites the sample, and then you can read on a detector the signal, the wave pattern, how that actually decays, that excitation decays. So again, IR does the same thing, where you just pulse it once with all of them, and then you use what's called a Fourier transform to kind of tease out the individual signals. And again, a Fourier transform it's like a calculus function. It's a way that you can like take the sum of a bunch of functions and then say, okay, this function is due to this function is due to this, and this part is due to this. And we're doing the same thing, except we're just kind of teasing out the individual peaks due to the different types of hydrogens that are there. I'll show you here. This is what you actually get out. This is what's called a free induction decay. This is what the detector reads. But like we can't really read this here at all. This doesn't really say anything to us. So we can't really tease out what this means. So we have to use a Fourier transform to figure that out. Yeah, so what tends to happen is you take like 8 or 16 FIDs, and then you average them all together. And then after that, you apply the Fourier transform. That just allows like any noise that's in there to get kind of weeded out just by averaging it out, and gives you like a cleaner NMR sample. Now, in order to take an NMR, the sample of your compound, your organic compound, has to be put into a liquid solution with a deuterated solvent. That just means all of the hydrogens in the solvent have been placed with deuterium. And then you're going to put that in the magnetic field. And then what you're going to do is you're going to spin it just so that you have like an average magnetic field in there. And just kind of like to smooth all the like individual things that could go wrong with your sample. So you have to use a deuterated solvent. And that's because you can't have any protons, right? Remember, protons, that's what we're looking for. So if we take chloroform and we just had normal chloroform in there, trichloromethane, we're going to see a giant hydrogen peak here from the CH here. And we don't want that. We want to look at our sample. So we use deuterated chloroform. So we just replace the hydrogen that's in chloroform with deuterium. Deuterated chloroform is the most commonly used because it's relatively cheap. There's only one hydrogen to replace. So like you can get 50 milliliters of this for something like $20, $25. On the other hand, sometimes though, like your sample doesn't dissolve in chloroform. So then that's no good, right? You need to find something else. You kind of slowly work your way up. Heavy water, D2O, is relatively cheap as well. You can get that relatively inexpensively. But then like for something like acetone, for example, acetone is, you've got 6 total hydrogens and you have to replace each of those with deuterium. So that's very difficult to do. And so acetone, you may have to pay, $100 for like 5 milliliters of it. I don't know it off the top of my head, but just an example, like these solvents can be very expensive. And this is what an NMR tends to look like here. I'll show you, there's a nice like video that I can link to that shows you what an NMR looks like and how it operates. We have a nice little tabletop version on campus, but that one doesn't really, it doesn't have the same magnetic strength as you can imagine as the nice big ones here with the superconductors. Okay, so now that's all like the background here. Practically speaking, like you don't really need to know that much about how the NMR is taken until you get to like physical chemistry. But for organic chemistry, this part is what's going to be really important. We're going to split up the NMR spectrum into 4 different characteristics. We have number 1, the number of signals. That's going to tell us something. We have the signal location, what's called the chemical shift on the spectrum. We have the signal intensity, which is the area under the signal or the integration. And then finally, we have the shape of the signal, or what's called the splitting pattern or the multiplicity. All of these things tell us different information about the electronic environment of the protons that we're studying. Okay, so starting from the number of signals. Okay, the number of signals in a proton NMR spectrum tells you the number of different kinds of protons that exist in a compound. Now, note, I didn't say the number of protons that exist, it's the number of kinds of protons that exist. If 3 protons, let's say, are symmetrical to one another, like in a methyl group. So like, let me just draw a compound here and you can kind of see what that's going to look like down here. So this methyl group, H, 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 this sigma bond here can rotate freely. So each of these hydrogens on average is experiencing the same electronic environment. So these hydrogens are not going to be different, right? They're going to show up in the same place because they have the same electronic environment. This is what we call chemically equivalent. Now we have 2 different types. We have homotopic and enantiotopic. We'll talk about that in a second. Homotopic protons exist when there's like an axis of symmetry that allows for one proton to be rotated onto onto another. So that's like what I mentioned with the methyl group. Methyl groups, those protons are always going to be the same. They're always going to be chemically equivalent. But these also are the case. So here we have an alkene. We have an axis of symmetry where we can rotate this. And we can see there's no like cis or trans or E or Z symmetry here because you just rotate one onto the other. There's that symmetry. Here, this homotopic protons, you just rotate the molecule. Once again, they're on top of one another. And then down here, same thing. There's a plane of symmetry or a rotational axis of symmetry here, axis of symmetry here. You rotate it, and then all of a sudden, it's right back onto the other one. So these are homotopic, and homotopic means they're going to have the same chemical shift. They're going to show the same signal. Now, one way that you can do it is you use what's called the replacement test. So this is where you take one of the 2 protons that you're trying to figure out, is this homotopic or enantiotopic? What you do is take the replacement test. You take one of the protons and replace it with deuterium, and then do the same thing for the other one. So here we take the top proton, it's a deuterium, and then do the same thing for the bottom one, bottom proton becomes a deuterium. Then ask yourself, what happened? What's the relationship between these 2 compounds? Well, in this case, you can just rotate this compound onto this compound. They're going to be superimposable. So those are the same compound. And because the resulting compounds are identical, that tells us that the protons are homotopic. Now, enantiotopic sounds exactly like that. So topic means making, right? And enantio would be like enantiomer. This is going to be the case if the molecule has a plane of reflection, and that makes one of the protons the mirror image of the other. So let me just show you what that means here. So here, this fluorine, carbon, chlorine plane here, these are all in the plane that I'm trying to draw here. This is going to give like a internal plane of reflection where this hydrogen would reflect onto this hydrogen over here. I hope that makes sense. You can also build this model for yourself if that helps us too. Now, if you do the replacement test, you replace, each of them here. So we replace the right proton first and then the left proton next. What we don't make the same compound, right? Because these aren't superimposable, but we do make a pair of enantiomers. Now, if you make these enantiomers, that means that you have made, these are enantiotopic protons. And if they're enantiotopic, they're going to be chemically equivalent. So these protons experience essentially the same chemical environment through symmetry, and so they're going to be chemically equivalent. Now, if none of that is the case, then you are at the point where you have protons that are not chemically equivalent, and if they're not chemically equivalent, then they're going to have different signals, and that's kind of the point here. You're generating more signals. So now here, the obvious way that this can happen is if you have these two protons here, they're both on a CH, they're both on the same carbon. You might think, okay, they're both on the same carbon, they probably have the same chemical shift. But do the replacement test. When you do the replacement test for the left one first and then the right one next, you don't end up with the same compound. And you don't end up with enantiomers. They're not reflections of each other, and they're not superimposable. So what you have is you have a set of diastereomers. So we need a different description to talk about these. These are what we call diastereotopic. And because they're diastereotopic, that means they actually experience different chemical environments or electronic environments. So they're going to have different chemical shifts or different signals. Now, one way that you can tell this is basically like, just look, is there another chiral center on the molecule? If you generate a chiral center and there's another chiral center on the molecule, when you do the replacement test, that means that you're going to have a diastereotopic set of protons. And then if you don't have any, if there's no other relationship between them here, then they're not going to be chemically equivalent. So again, only homotopic and enantiotopic protons are going to be equivalent. In this case, we have a set of two protons, exactly what I told you, and we have a chiral center, right, in this 2-butanol. So we have a chiral center. When we replace either of these protons, we're going to get different stereoisomers or diastereomers when we replace either of these with a deuterium. So that means that they're diastereotopic, and that means that they're going to be different signals. They're going to give us a different set of signals. Yeah, so I just told you exactly this shortcut. Again, here's your shortcut. There are two protons on a CH2 group will be equivalent. If there are no chiral centers, that's what we have on the left. They will not be equivalent, however, if there is a chiral center. Now, you can tell yourself this because, like, check this out. This hydrogen is pointing the same direction as this OH group. The nature of this OH group is going to change the electronic environment on its neighboring hydrogen here. So in other words, this hydrogen just experiences a different chemical environment than this hydrogen, which is pointing on the other side. Okay, now the 3 protons in the methyl group, always equivalent. I told you that one already, but that's important as well. And then finally, multiple protons can be equivalent if they can be interchanged through a rotation or a mirror plane. So here is 3-pentanone, for example. 3-pentanone has an axis of symmetry here. So that axis of symmetry can rotate one way or the other. And that means that the methyl protons here and here are equivalent, and these protons here are equivalent as well. So when we count up the number of signals here, we're going to get one set of signals for these carbons. I'm sorry, for these hydrogens, and then we're going to get one set of signals for these hydrogens here. So that means we're only going to have 2 signals in this case. Hold on, let me put my annotation. Okay, all right, so now let's go ahead and do this. What I want you to do is we've marked these 3 compounds as HA and HB, and this question is particularly about HA and HB. I want you to tell me, are these enantiotopic, homotopic, diastereotopic, or in other ways not chemically equivalent? And then tell me how many signals you would expect to see in that compound's NMR spectrum. So give it a shot. I'll do the first one with you here, so that'll maybe help anyway. Okay, so HA, HB on this first one. This is just pentane here. Okay, so let's go ahead. Now, if we do the replacement test, so we would have a D in the background going back, or we would have a D in the front like that. What I can tell right away is if we rotate this molecule, 180 degrees, we're going to end up with the same molecule on that side. So that means that we have homotopic protons here. So these are homotopic. So that means that these are going to have the same signal. Now, the question then becomes, how many other signals are we going to see? So here, H and H, H and H, 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 and then over here it's H3. I'm just going to put these as H3, H3, H, H. Okay. Now, we figured out already that there's an axis of symmetry here, right? If we rotate the molecule, it's going to be the same, on both sides. So that was what kind of led us to believe that, this is going to be our first signal here. Now, as we move out from there, that axis of symmetry still applies. Like this set of protons and this set of protons, they're still on the axis of symmetry relative to one another. So this is going to be the same signal. So we're just going to call these both signal 2. Now, I hope you can see where this is going from here, because the same thing is still true as we move one further out. When we rotate this molecule, these carbons and hydrogens are going to line up on one another. So that gives us our third signal. And then finally, out here, we got our 2 methyl groups. That's signal 4. So I count 4 signals, and the answer was those were homotopic and 4 signals. Okay, now give it a try. We've got a bunch of, we got 2 more here. These are the harder ones, so don't worry, pause the video, and when we come back, we'll show you how to answer this question. So give it a shot. I'm gonna go ahead and pause. So let's take a look here. Starting up top, we got HA and HB on the second one. If you do the replacement test, you end up with a pair of enantiomers, so that's enantiotopic, and that means they're gonna have the same signal. So now we're going down the list here. We've got 1 signal on this methyl group, 2 on this alkenyl hydrogen, 3 over here, 4 for both of these, 5 for the carbon hydrogen on this one. And then now that we look at these here, we can see that these are symmetrical as well, right? So if we were to do the replacement test here, we would end up with a pair of enantiomers again. So what that means is like these are symmetrical to one another. They're in the same chemical environment. This CH2 is going to have the same signal as this CH2. So that's 6, that's 7, and then this last one back here is number 8. So I count 8 total signals in the NMR spectrum. Okay, now this one is the messy one because here HA and HB are diastereotopic. Remember, there's a chiral center and we're looking at a CH2 group. So that means there's already a chiral center. This is a CH2. These are diastereotopic. And the crazy thing is not only are these diastereotopic, we have CH2s all the way around the cyclohexane ring that are also diastereotopic. So counting the number of signals, we get 1, 2, 3 from the first diastereotopic set, the H on the other chiral center, plus the H here from the cyclohexyl ring. And then each of these represent 2 signals as well. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I count 15 total signals on that carbon, or on this HNMR spectrum. So yeah, that'd be pretty crazy. Fortunately, we don't have to analyze that one yet, but we'll get there. So there you go. All right. Oh, now one thing that's kind of cool about the number of signals too is you have to keep in mind that one thing is like a lot of chemical processes, including like rotational and vibrational and then chair flips as well, occur very fast at room temperature. But if you have like a very low temperature NMR, you can actually kind of freeze out one or the other. So for cyclohexane, for example, cyclohexane has 2 different sets of protons. There's the axial protons and the equatorial protons. These are different electronic environments. Like they're just the ones up here are experiencing diaxial interactions, 1,3 diaxial interactions, and the equatorial ones don't have that same issue. Yet, when we actually look at the NMR spectrum, so you would expect to see like 2 different NMR spectrum, 2 different types of protons in the NMR spectrum. We only see one because basically they're just flipping between axial and equatorial too fast for us to see. Now, if you reduce the temperature, negative 100 degrees Celsius is possible. Remember, the magnet itself is at like 4 Kelvin, so it's relatively easy to reduce the temperature inside the NMR. The ring flipping goes slow enough that you can actually observe those two signals. Okay, so that's the number of signals. Now, the next thing we're going to do is we're going to talk about the chemical shift. Now, chemical shift is just kind of a way of saying, okay, it's a way of like giving us a number on the x-axis, like below the NMR spectrum, a way of like counting one from another. And we calculate this proton shift. It's calculated relative to something else. And in particular, what we do is we look at the difference between the chemical shift of the proton that we're looking at and compare it to tetramethylsilane, or TMS. So now you can see here, this is a silicon in the middle, and then 4 methyl groups around it. So this gives like a characteristic signal. And this characteristic signal we're going to call is basically the zero. Now, if you take benzene on a 300 megahertz instrument, you get a signal 2,181 hertz. You divide it by 300 megahertz, that's 300 times 10 to the 6 hertz. That gives you 7.27 times 10 to the negative 6. Now, that's not particularly useful. We return it, we report these in terms of parts per million. So we're going to end up dropping this 10 to the 6th here, and ended up as 7.27 on our actual scale here. Yeah, so one thing to point out here is that the strength of the magnet can basically vary from one instrument to another, but the relative shift will remain the same. And that's why we use this relative shift compared to the observed shift, because we want to make sure that it's the same between different instruments. Right, so because the hertz and hertz cancel out, we end up with a dimensionless unit. We use this delta here to represent it. And we give these units in parts per million because it just is going to get rid of that 10 to the 6th number that we have. The proton signals that we're going to talk about, almost all of them come between 0 and 10 parts per million. A handful come below 0, and then just a handful come above 10. But 99% of the time, you're going to see your proton signals between 0 and 10 parts per million. Okay, now here's what this is what a spectrum on a proton NMR actually looks like. Let me make this a little bigger on the screen so we can see it a little better. There we go. So basically, if you have your shift occur at low field strength, that's what we call downfield, and that's on the left side. If it occurs at high field strength, close to the TMS, that's what we call upfield. The more shielded your protons are, the stronger the external magnetic field is going to be in order to excite, to get you that same energy from the deshielded protons. So on the left side, we have the deshielded protons. Those are the ones that have lost electron density, usually due to the presence of electronegative atoms. And then upfield, we have the shielded protons. So these are like in nonpolar bonds, like carbon-hydrogen bonds. That's what we expect to see down here. Right. So again, now NMRs that we talk about now, they use a constant field strength. And then you just kind of irradiate a particular, you irradiate all the radio waves, and then you tease out the individual signals using a Fourier transform. But here's the big kind of like takeaway here. The protons that are closer to tetramethylsilane, the upfield protons, these are more shielded, and because they're more shielded, they take less energy to flip. So that's what we see down here. The higher energy ones, those are the ones that have been deshielded. Their electrons have been taken away, and so they're feeling more the strength of the magnet itself, the magnetic field itself. So they're harder to shift. It takes more energy. So it's still more energy on the left, low energy on the right. Okay, so I mentioned this already, but protons will be deshielded when there's a nearby electronegative atom. Remember, electronegative atoms are electron hungry. So they're going to pull electrons away from neighboring sigma bonds as much as possible. So like methane has one set of protons. Those protons show up at 1.0 parts per million. Add in an iodine, which is slightly deshielding. It's more electronegative than carbon. It's going to pull electron density away from these carbon-hydrogen bonds. which is going to expose these protons more to the external magnetic field. So it shifts from 1.0 to 2.2 parts per million. Increase the electronegativity, so going up the halogens here from iodine to bromine to chlorine to fluorine, you go from 2.2 to 2.7 parts per million to 3.1 parts per million with the chloromethane, and then 4.3 parts per million with the fluorine. So the stronger the electronegativity, the more electron density that this neighboring electronegative atom is pulling away from these hydrogens, the more downfield, or the higher the parts per million is going to be. Additionally, you can also add additional electronegative atoms. This probably makes more sense, but the more electronegative atoms you put on there, the more electron density is going to be sucked away from that hydrogen. So the higher, the more de-shielded that atom is going to be. So, and this also like diminishes the further away it is, right? So an alpha carbon is going to experience the greater effect from the bonded chlorine, whereas the beta carbon has just a small effect, and then the gamma carbon really doesn't experience anything. So, okay, so in order to predict what the chemical shift for a compound is going to be, or for a hydrogen is going to be, I should say, start with what type of proton you have. Now, these are old words here, but I'll try to explain it in like how we've talked about things. So you have the methyl group. Now this makes sense. It's just when you have three hydrogens all bonded to the same carbon, that's a methyl group. You're probably familiar with that. Now, if you have a CH2 that's like in between, two other carbons, or like you could be an OH group down here, could be anything. This is what we call a methylene group. So this is, again, old words for this, but we have the CH2. This is a methylene group. That has a standard chemical shift of 1.2 parts per million. And then finally, methine. Methine is essentially where you have like a single hydrogen bonded to like a tertiary carbon. And that chemical shift starts at 1.7 parts per million. So these are your standard ones. You say, okay, I have a methyl group that starts at 0.9 part per million. Then what you're going to do is go to the next table, and that's going to tell you how you adjust it. So if you have oxygen or an oxygen from an alcohol or an ether, what that's going to do is for the protons that are alpha to it, that's going to add plus 2.5. So if you have a methylene group here, so this is CH2, that's neighboring an OH, it's 1.2 parts per million plus 2.5 parts per million, that gives you 3.7 parts per million. Now, on the other hand, this oxygen for an ester, that is even stronger, actually. That adds plus 3. So if you're neighboring the oxygen on the ester, that adds about plus 3. So you take, in this case, it's a CH2, right? So it's a methylene group. So 1.2 parts per million, then you add the 3 parts per million for the ester, oxygen ester, and that gives you 4.2 parts per million. And it's a pretty good predictive property. It's not 100%, but it just gives you an idea of where you might expect to find these here. And then the other one here is the carbonyl group. So if you have a neighboring carbonyl group, that adds about plus 1 to the alpha protons. So here we have a ketone. So the hydrogens that are on the carbon next to the ketone get about plus 1 parts per million. In this case, it's a methylene group that starts at 1.2 parts per million. You add plus 1 parts per million, you get 2.2 parts per million. And so that's where you predict, and it's not too far. Okay, so go ahead. Let's go ahead for this set here. Tell me which ones are going to appear the farthest downfield, and so which 1, 2, 3, or 4 is going to be the furthest downfield. And then let's go for the top one here. Just predict where those chemical shifts are going to be based on what I just said. So I recommend go ahead, pause the video, try to figure out which one's going to be the most downfield, then figure out how are you going to apply what you just learned, and then we'll go ahead and go through this nasty one down here together. Okay, so give it a shot. I'm going to pause the video. All right, so let's go through the results here. So on the top one, hopefully it's pretty clear that the protons on number 4 are going to be the most downfield because they're closest to the OH group, right? And sure enough, if we do the math, like this is, CH2, it's methylene, it's neighboring or alpha to alcohol oxygen. So that's plus 2.5, you end up with 3.7 parts per million. The neighboring one, now this is the beta carbon. Remember, the effects on the beta carbon are about 1/5 that of the alpha carbon. So it's 1.2 plus 1/5 times 2.5. That ends up 1.7 parts per million for that methylene group. Now, once we're here, these are, farther away, gamma or less, so we don't have any effects here. So carbon 2, that ends up being just a methylene group, 1.2 parts per million, and then carbon 1 is 0.9 parts per million because it is a methyl group. Now, it gets a lot trickier on the second one down here. So what I did first is I went ahead and listed, okay, here's a ketone, that's a +1 for the neighboring ones. This is an ester oxygen, which is +3, another ketone +1, and then down here, fluorine plus 3.3. So we just kind of went through. So carbon 1 is alpha to this ketone, so that's +1 for its hydrogens. And then it's also beta to this ester oxygen over here. So that's +1/5 times 3, that's 2.8. Carbon 2 is alpha to the ester oxygen, so I give that one a 1.2 plus 3. And then it's also beta to this ketone over here, so that's 1/5 times 1, that's a 4.4 parts per million. Now we skip over here to carbon 3. Carbon 3 is alpha to this ketone and also beta to this ester. Now, I'm not confident that this is the right way to do this assumption, but I can't really tell you any other way other than this is beta, so we'll just go ahead and give it the beta effect here. So it's going to be 1.2, because it's a methylene group, +1 alpha to this ketone, or the carbonyl basically in the ester. And then it's beta, so +1/5 times 3 to this oxygen. It's also beta to the fluorine. Now the fluorine has a really big effect. That's +3.3. So we take times 1/5 plus 3 times 3.3. That gives me 3.5 for that parts per million when I add everything up. Then finally, carbon 4. Carbon 4 is a methylene group, so it's 1.2. It's alpha to a fluorine, that's +3.3. And then it's beta to a carbonyl, so that's +1/5 times 1. That gives me 4.7 parts per million. So I believe that should be the winner. I'll hear arguments, if you disagree, but I think that is the case. This is how you would do that math in any case, and that is how you would come up with the answer there. So I hope that makes sense. Okay. All right. Now there is one other type of effect that can move your signal even further downfield that you wouldn't expect, which is something that's called basically if you have a conjugated pi system, when those conjugated pi electrons are subjected to an external magnetic field, they can actually circulate within the aromatic system. So like within the benzene ring, for example. And so that means that you're going to have an induced magnetic field. Anything outside the ring of electrons, pi electrons, is going to be further deshielded. Anything inside that would be shielded even more, in fact. This is what's called diamagnetic anisotropy. And the basic application is going to be for benzene rings. That's the main thing that we want to be able to identify here. So protons, so this is clearly a benzene ring here. Protons that are on the outside of it experience basically an increased magnetic field. So they're going to be moved downfield. So here's basically what happens. Even though these hydrogens aren't involved in any polar bonds, and there's no polar bonds on this molecule whatsoever, these aromatic protons show up all the way above 7 parts per million. So usually between 7 to 8 parts per million, that's where you're going to see these aromatic protons. That's just another thing to kind of keep in mind there. And yeah, it's basically just like deshielding, and it's only going to happen for our aromatic protons. So just kind of keep that in mind. Now it can occur on the inside. This is kind of a rare example of this. This is not something that's going to come up here. This is aniline. It's another aromatic system. If you have protons that are inside the ring here, they're actually going to be shielded on the inside of the pi system, and they're actually going to show up at around -1 parts per million. So it's kind of rare, but you do see in the negatives in this case here. Okay, and so here's your chemical shifts. This is just going to give you an idea of where these start. So like methyl, methylene, methine, we already talked about that. An allylic chemical shift is going to be around 2 parts per million. Alkynyl would be around 2.5. So this is on a terminal alkyne. If you have an aromatic methyl group, so it's almost like a benzylic position, you can think about it, that shows up at around 2.5 parts per million. If you have an alkyl halide, this is going to show up in the range of 2 to 4. This is more like giving you the ranges on this side here. These are like the starting points. These are the ranges that you're going to see things. Alcohol protons tend to be in the 2.2 to 5 range. Vinylic protons should be 4.5 to 6.5, depending on the environment. Aryl protons, those are the aromatic ones we just talked about, 6.5 to 8. Aldehyde shows up at around 10, And then carboxylic acid, if you can see it, shows up around 12. Okay, so that's the chemical shift. That's like one of the big ones there for, reading these NMR spectra. But it's not the only kind of information that we can get. We can also get from the integration of the chemical signal, we can actually get an idea of the number of protons that give rise to each signal. So it's basically the size of this integration is going to tell us how many protons relative to one another are in this peak. So here, if we get an integration of 27 to 40 to 28 to 42, this is telling us basically that, well, let me just show you here. You set the smallest one equal to 1.00. And what that means is, like, you say, okay, this is one proton. I'm just going to say this is one proton. And what do you get? Well, you take 40 divided by 27, that gives you 1.48. 28.4 divided by 27, 1.05. 42.2 divided by 27, that's 1.56. So this gives you an idea of the relative number of protons. Now, you can't have half a proton, right? So you can't have a 1 to 1.5 ratio. But what is that ratio equivalent to? Well, if you set this one to 2, then all of a sudden you get 2 to 2.96. That's pretty much 3. So it's like a 2 to 3 to 2 to 3 ratio. And that actually makes sense. So this is how you learn about, like, this is how you can learn, like, how many protons are, available, or how many protons are assigned to each signal, is through the integration. Now keep in mind that your symmetry will also affect you here. So you'll get a 2 to 3 ratio here, but remember that this 2 to 3 ratio represents 4 hydrogens on the one next to the ketone, and then 6 on the far methyl groups there. So just keep that in mind, that you still get 2 signals, you get an integration of 2 to 3, but it's actually 4 to 6. Just keep that in mind. Like, and that makes sense, right? It's just like the 1 to 1.5 thing. We don't know the absolute number. It's not like the compound says, hey, I just got 1 proton here. You can only know the relative number of them from the integration. Okay, so that's the integration. Again, that tells you the number of protons that are in each signal, or the relative number of protons under each signal. The splitting pattern, or what's called the multiplicity, actually gives you further information on the number of possible neighboring protons that a given proton signal has. So this is how signals are going to show up in the NMR. You can have things that are a singlet that just shows up as 1 peak. A doublet has 2 equivalent peaks. A triplet has 3 peaks, and the center one is the tallest. A quartet has 4 peaks. The outer 2 are small, the inner 2 are big. A quintet is 5 peaks, and it kind of follows like a mountain pattern, right? It's like small, medium, big, medium, small. A sextet is like small, medium, big, big, medium, small. And then a septet, it goes on and on and on like that. So these are the types of signals that we can actually see in the NMR. And so I don't know, it's really fascinating. It's kind of beautiful in a way, but there's a lot of information we can also get from these signals. Okay. So multiplicity is going to come from the fact that when you have neighboring protons, remember, we're studying like the magnetic effects here. And the magnetic fields that are generated by the angular momentum of the protons are going to affect each other as well. So like here, if we have HA and HB, we have 2 methine peaks here, 2 methine protons. The protons themselves are going to align with the magnetic field, and they're also going to be affected by the fact that this HB could align against or with the magnetic field. So think about it this way: if HB aligns against the field, or HA aligns with the field, then HB could align against it, or it could align with it. That's 2 separate positions and 2 different magnetic environments that the HA is going to face. And so that shows up as a doublet. Now it gets more complicated. What if there's a methylene group next to HA? Now all of a sudden, not only do you have your HB that you talked about before, but now you have another HB there as well. So these HBs could be, so if HA is up, well, HB could be up, up, or it could be down, down, or it could be up, down, up, down, or down, up. Now, these are the possible environments, and check it out. If both protons are aligned against the field, that's one environment. Both of them with the field, that's another environment. And then there's 2 possibilities, with one against and one with. So because there's two possibilities that one is aligned with and one is against, that's a more likely scenario than both of them aligned against and both of them aligned with. So we actually see that this central one here is a bigger peak. It represents more likely that the HA is in the environment where one HB is with and one HB is against. Okay, now you look at it with three, and then you have a quartet, right? So this is where you have all three against, all three with, and then you have a combination, one with, two against, or two with, one against. And this also kind of explains why we see the quartet pattern as like a small, big, big, small pattern, because the small patterns only represent one possibility of the alignment of the HBs, whereas the big patterns represent three separate alignments of the HBs. So they're just more likely to occur. And then you can look in your book, there's more pictures as that goes on. But that's kind of like what you need to keep in mind. So basically, we don't just have the alpha and the beta spin state. We have to consider the spin states of the neighboring protons as well. Okay, now, here's the good news. If you have n neighboring protons, and those neighboring protons are all chemically equivalent, you will have n plus 1 peaks in the signal. In other words, you have three, say you have a proton next to a methyl group. And of course, it's a methyl group. Those protons have to be chemically equivalent, and there's no protons on the other side. That HA is going to be split by those three. So that gives 4 signals. That's an easy way to think about it. It's like you have 3 neighbors, so you get 4 signals. So here's the deal. Equivalent protons cannot split one another. They resonate together. They're going to be in the same signal. They don't split each other. And then in order for a proton to split each other, they have to be within a 2 or 3 bond distance. So like you can have geminal or vicinal protons split each other, but if you have things that are too far apart, they're not going to split in that case. So geminal, that means it's like, think like Gemini, like the twins. That's where they're on the same carbon, HA and HB. So this would be the case where they're diastereotopic, they can split each other. Or vicinal, this is the more common thing that we see a lot, is where HA and HB are on neighboring carbons, then yes, they will split each other there as well. But any further than that, can't happen. Okay, now keep in mind the n plus 1 rule only is going to apply when all the protons that split are going to be equivalent. So like keep in mind here, like as you look at this one, so draw in your neighboring hydrogens here, right? This is our HA. Well, this is HB and this is HC. These don't resonate together, so they're not going to split HA the same. In fact, they're each going to have their own individual split. So rather than seeing, in this case, you would say, oh, it's a triplet. Nope, nope, do not use that rule. The n plus 1 rule does not work here. Instead, HB splits HA into a doublet, and then HC splits HA into a doublet again. So you get a doublet of doublets. So you'd end up with what looks like 4 peaks, hopefully. And that's in the simplest case. It might be even more complicated. But we'll talk about that in a little bit. Okay, now the strength of the splitting is going to be what's called the coupling constant, and you measure the strength by calculating basically the distance between the individual peaks. So the coupling constant is really useful because if you have a pattern here, so we have a quartet pattern and a triplet pattern. The quartet pattern represents this HA methylene group, and that's split by a methyl group, the HBs here. That's great. Now, the distance between the 4 peaks in the quartet they're equidistant, I should say. It's this JAB distance here. Now, its neighbors, the HBs, they're a methyl group, and they're split by the neighbor methylene, the HAs. So you'd expect these to be split into 2 plus 1, 3 peaks. So you get a triplet. Now, what's really cool is the distance between the peaks for B, so this triplet peak here, JAB, JAB, it's going to be the same distance for B as it is for A, because the coupling strength is the same. Because you're dealing with like how much, think about it this way, it's like how much does B affect A and how much does A affect B? Well, that's just like when, think of it like tug of war. It's like, how hard are you pulling on the rope? How hard is your friend pulling on the rope? If you're balanced, then you're like balanced in the middle. That's a bad example. Maybe, oh, how about this? Like when you push against the wall, right? Think of it like Newtonian force. You push against the wall. How hard does the wall push against you? it's equal and opposite, right? So it's equal and opposite splitting, so you get the equal and opposite coupling constant. It ends up being just the same distance. And yeah, this is what's called the J value, or the coupling constant. And you just measure it by like drilling down, you zoom in, and then you see, oh, what's the distance here? And that'll tell you how big that, how closely related those two magnetic fields are. Okay. And now, one reason we mentioned already that the higher field strength instruments, you end up with the same parts per million shift, but you can get better resolution the stronger the magnet is going to be. So like the NMRs that we have in lab are usually like 10 to 50 megahertz, like in our community college labs. If you go to like a research institution like UCSD, they actually have like a 900 megahertz NMR. And then for protein NMRs, I think it's like 1200 megahertz. I got to double check, but it's just like an extremely strong magnet so that you can get good resolution on these individual peaks. And then, so as you can see on the left, it's a lot easier to measure where that's going to be, like the coupling constant between these peaks here, right? Because you can see this one's clearly here, this one's clearly here. Whereas here, you just don't get that kind of resolution. Yeah, and then, so one thing to point out is like the pattern that we just talked about, quartet triplet, that's a really common pattern that we see because this is like an ethyl pattern here. This ethyl pattern involves like you have a CH2 group, a methylene group that's bonded to a methyl group. So 2 hydrogens integrate here, 3 hydrogens integrate here. This is a really strong signal that you have a ethyl group. Now, on the other hand, we can see that here as well because the coupling looks about the same, right? The distance between the peaks on the triplet look about the same as the distance between the peaks on the quartet. On the other hand, if we have something that looks like this down here, clearly the distance between the quartet is like, it's like twice as wide as the distance between the triplet. This can't be an ethyl group, or at least the peaks that we see here can't be an ethyl group because this coupling constant is different from this coupling constant here. So these aren't pushing on each other with the same force. Okay, so just a couple other patterns that you're going to see as you look at multiplicity. If you have a singlet peak, so just no splitting whatsoever, that integrates out to 9 protons one way or another, that's a pretty good indication you have a tert-butyl group. Tert-butyl groups have 9 chemically equivalent protons and no splitting. So it ends up just being 9 protons. Isopropyl groups have a really cool signal. If you have an isolated isopropyl group, you get a doublet that integrates to 6 protons because you have your terminal methyl groups split by the hydrogen on the first carbon on the isopropyl group. And then this one actually, because it's split by 6 chemically equivalent protons, ends up as a septet. It gets even more complicated, obviously, if there's more protons over here, but it's just kind of fun to look at. Okay, all right. Now, complex splitting, or this like complex patterns that you can see here, and I already mentioned this very briefly. This is when you have different kinds of neighboring protons. So like HB here. HB is split by HA, right? And if you were split just by HA, you'd expect it to get into a quartet. On the other hand, it's also split by HC. So you see that HB is split by HC, and that would give you triplets because it's split there. Now, the way that this pattern is going to look depends on the coupling constant. If the coupling constant from A to B is stronger than that from C to B, that means that it's going to split into a quartet first, and those are going to be the widest peaks. Then those quartet, each of those is going to be split itself into a triplet by HC. So this gives you a quartet of triplets, right? That's pretty crazy. Now, on the other hand, it could be the case that HC has a stronger coupling constant, so you get split into a triplet. Then what would happen is HA splits it again, and then you get a triplet of quartets. Now, so this is the example here of a triplet of quartets. Kind of cool looking, right? So you can see these kind of complicated signals. And sometimes you can see these. This is very rare that you're actually able to kind of like identify these. Sometimes you need like a really good NMR in order to do that. Now, on the other hand, a lot of the times, everything's going to overlap, and especially on the NMRs that we use. So you end up just with something that's called a multiplet. It's just this giant mass. And the only really useful information that you can get from it is, well, first off, it's complex splitting. And then, the integration is still fine and the chemical shift will still tell you a lot as well. Additionally, we don't always see splitting for protons. For example, when we take the proton NMR of ethanol, we have a proton that's on the oxygen here, and that integrates to 1, and it shows up at around 2.2, I guess. And if we ask ourselves, how is this one going to be split? Well, the neighboring carbon has 2 hydrogens, so should it be a triplet? But that's not the case. This hydroxyl proton actually undergoes hydrogen bonding, and as it goes on hydrogen bonding, it can be exchanged. So it's not coupling to the neighboring carbon protons enough for it to actually be split on our NMR. Again, it was just trace amounts of acid from anything in ethanol or whatever. This could be an example of a place where you just don't have a consistent proton to measure, so there's no splitting possible. Okay, now here's the important one, using proton NMR to distinguish between compounds. So let's look at these 3 different types of xylene molecules. That's dimethylbenzene. 3 different molecules would have basically the same IR. They're the same, carbon-carbon double bonds, the same aromatic peaks, and the same number of carbon hydrogens that are all sp2 carbon hydrogens. So we couldn't use IR, and we couldn't use MS, which we haven't talked about, but don't worry, you can't use MS. They all have the same molar mass, so you can't use that. But NMR can easily distinguish it because it gets the different number of signals here. On the left one here, where it's like a 1,2 methyl, 1,2 dimethyl, you have 1, 2, 3 possible signals due to symmetry. The 1,3 dimethyl has 1, 2, 3, 4 signals, and then the 1,4 dimethyl has 1, 2 signals. So easy to distinguish between by proton NMR. Here we go. So here's what you need to do when you analyze a proton NMR spectrum. So step 1, calculate the degree of unsaturation, or what's called the hydrogen deficiency index. So this is what we used way back in chapter 2, I believe it was, or it could have been even chapter 4, where we talked about alkanes and how to figure out if something's an alkane or not. Then once you have that, consider the number of signals that you have and the number of protons that you have. The number of signals will tell you basically the symmetry of the molecule, and then the number of places where you can kind of try to figure out where those signals are coming from. So then once you've got like each signal, like as you're looking at each signal, try to draw a fragment that is consistent with each signal. So like if you have a signal that integrates to 3 and it's a triplet, that's a pretty good indication that you have a methyl group that's being split by a neighboring methylene. So it may be that you have an ethyl group. So try to put that together. You have a CH3 neighboring CH2. And then what you're going to do is just slowly tease out the fragments. Try to put them together into a structure that's consistent with all of the possible spectral data. Oftentimes you'll combine NMR spectroscopy with IR or other types of spectroscopy to help you figure it out. Okay, so let's go ahead and give it a shot. I'm going to let you try it first, and then I'm going to walk you through the answer here after you've given it a good shot. So this is an NMR spectrum, and then I've given you 4 possible candidates here. So given these 4 candidates, which of them is consistent? Now keep in mind, I give you a little extra data here. The IR spectrum shows a strong absorption at 1800 per centimeter. That's a big clue. And then knowing that, ask yourself which of the following structures is consistent with that spectrum. Okay, give it a shot. I'm going to pause the video. I'll do a little bit of workup here, and hopefully when we come back, we can kind of talk it through and we'll get to the answer. All right, so I've worked partway through this, but I want to kind of like get to the final answer with you here together. So first, start off by add up the integrations first off and see, does it match the number of hydrogens that you have in your answer, right? So we know there's 15 hydrogens in this compound, so we've got 1 plus 4 plus 2 plus 2 plus 6. Sure enough, that's 15. So we don't need to worry about the integration. That's still the case. This represents 1 proton. This is 4, 2, 2, and 6. Now, do you see any patterns that might be useful? I kind of already wrote it out, but you notice right away, you have a 4 to 6 split here. That's very interesting because this 6 one looks like a methyl group that's split by an ethylene proton. And then this one over here, 4 to 6, actually looks like it's, again, 2 methylenes basically split by this methyl group over here. So that's really important. Another thing to keep in mind is we have a carbon-oxygen double bond. We don't have any oxygen-hydrogen bonds, so there's no alcohols. There's a chlorine that's terminal on one end. That's all information that we get from the molecular formula plus the IR, basically. Okay, now as we look at these other peaks here, we notice a couple things. So here we have a methylene group. It's integrating to 2, and it's split into 3 here. So let me actually let me change this just a little bit, because we don't really know if this is a methylene neighboring a methyl. We're just going to kind of put a question mark there. We can't really tell based on the splitting or integration on how that goes. It could be a multiplet. Now this one does seem to be just a triplet. So that would be, and it integrates to 2. So it's a methylene neighboring a methylene. And then finally, we have a single proton that neighbors a methylene. So now, based on what we have, the biggest clue that we have, I think, is that we have 2 equivalent ethyl groups. And furthermore, this ethyl group has to be neighboring something that doesn't split it. So like this methylene part here, if this were split further, we would get a complex splitting pattern down here. And that's not the case. So let's go ahead and look at our possible answers here. We need basically symmetrical ethyl groups. So here, where's my drawing? There we go. Okay, so here, so just starting over here, we see these ethyl groups, and sure enough, they're symmetrical, right? They're both bonded to this carbon here. So I think we can say those are symmetrical. Same thing here, this ethyl group, and they're both bonded to that, so that's symmetrical. That's good. Now here we have 2 propyl groups that are symmetrical, but we know that we can't have a propyl group because then this would be split further, right? This would be now like a triplet of quartets or a quartet of triplets, and that can't be this case. And then down here we have this ethyl group and this ethyl group, but they're not symmetrical, right? This is closer to the carbonyl, so this is going to have a different chemical shift, so that can't work. So these all have these both 3 and 4 have chemically equivalent carbonyl groups. And so that's kind of where we want to focus here and try to figure out. Okay, so now let's go ahead. The next thing I want to look at is this hydrogen here, right? So this hydrogen here and this hydrogen here. We see that one at like 4.2 down here. And this 4.2 peak is split into a triplet, more or less. It might be complicated, but it kind of just looks like a triplet to me. This is a really low resolution NMR, so it's kind of hard to tell anyway. So what that would suggest is it's split by a neighboring methylene group. So here, let's take a look at this proton on number 3. Neighbors an oxygen, and then a carbonyl carbon. None of those are enough to split this hydrogen here. So that means that there's no possible split here. This should be a singlet. Over here, on the other hand, this neighbors a methylene. So sure enough, that should be, so we'll call this A. That should be split into a triplet. That's what it looks like, is A over here. Okay, so let's wrap it up. I'm just going to show you the rest of these here real quick. So we already found B and C, right? So we'll call these B and C. We know that C is right here, B is right here. Now we're just kind of splitting these up. So we have a triplet and then we have a quartet. So now this quartet, I mentioned before, it looks a little complicated. And sure enough, I think the only compound that can be this one here has to be this one here, because it's neighboring a pair of protons here with the methylene and then one of the methynes here. So that works out to being about a quartet. So that matches up pretty well. And then finally, the E protons, those have to be the only remaining ones. This methylene, and sure enough, it matches. It's a methylene group, it integrates to 2, and it's split by a neighboring methylene group into a triplet. So there you go. It has to be number 4, cannot be 1, 2, or 3. Okay, I hope that helps. Now, one thing is you're gonna really wanna practice this stuff, right? So get to practicing. We'll talk about carbon NMR next, which is a whole other thing, but we'll go through it much simpler. We don't have to worry about splitting there really with the carbon NMR. So yeah, okay, well, thank you so much. Get some more practice and I'll talk to you soon.